Ladies and gentlemen, boys and girls, children of all ages, it's time for us to begin the notes for pages 3 and 4. Yes, that's right. Our second day of real math. And so we want to start you guys talking about is real number properties. And so essentially, when we're talking about real numbers, this is probably something that you talked about maybe in an earlier algebra class, but I want to make sure that you understand what it is that we're talking about. So up in a little bubble up here, we've got a little definition of what real numbers actually are. So a real number is essentially any number that you have ever been able to think of for real. That's kind of a terrible way of saying it, but it does sort of work. So we got positive numbers, negative numbers, any fraction, any terminating decimal like 0.33333333. And then when we talk about something like this, in fact, irrational numbers are real numbers. An irrational number is a number that's got like pi is like the most famous irrational number. So when we talk about that, that's a number that goes on and on forever and doesn't repeat. But all of that stuff put together counts as a real number. It's basically any number that can exist any place in the real world. And so we got a bunch of rules that we can follow anytime you're dealing with those. Now, you guys are in Algebra 2, which means we will eventually add another type of number to these called the imaginary numbers. But that's kind of like a preview for something you're going to be seeing second semester. So look out, you'll be excited. Okay, so what we're going to be talking about today are three properties that we sort of go along with in explaining how some numbers will work with each other. And these are the commutative, and you see we have this little bus here to commute, to go from one place to another. The associative, which means we associate two things, so we've got two hands that are kind of shaking each other. And the distributive property, which means we are distributing from 1, 2, and 3 things. Now, you're familiar with a bunch of these. The one you're going to use the most is the distributive property, and we'll talk a lot about that. But we do want to make sure you understand the commutative property and the associative property as well. So the commutative property, it essentially just means if you're adding or multiplying, the order of this doesn't matter. It'd be a plus b and b plus a. Those are exactly the same thing, just like a times b and b times a. If you flip them around, it's not going to matter with something like this. And the reason they call it commutative is because commuting means to move from place to place. And so it means with adding or multiplication, you can move the numbers from place to place and it's totally fine. So if I have like 7 times 3, you guys know that's 21. Just like if I do 3 times 7, it's also 21. So that's the commutative property. And I tend to remember that because we're talking about moving from place to place. That's the commute. The associative property, this is one where it basically is telling us when we have 3 things that are going together, if they're all doing the same thing, adding or multiplying, it doesn't matter if you start with the first 2 or the second 2, you're going to get the same answer. And so what I want to show you with this is let's just do 3 numbers added because I think that'll be fine. Let's go 5 plus 2 plus 3. Now, if you're anything like me, you looked at this and said, okay, I'm going to pick 2 of these numbers together and add them and then add that to the third one. Now, for me, I always choose the smallest 2 and say, okay, I took 2 plus 3 together and in my head, and I got 5. And then that 5 plus 5 gives me a total of 10. Pretty easy. But if you didn't do that, it's possible you instead said, well, I actually grouped this 5 plus 2 together first, which would give you 7. And 7 plus 3 is also going to give you 10. So what the associative property tells us, it doesn't matter which 2 are associated with each other. You can kind of get to this into a place where you can see what it is. Now, the way that I tend to remember this rule is probably less clean than people would like. But you know, what the heck? You guys are watching a video, so that's fine. When we look at something like this, I look at the word associative and I try to think of what is the base word for this that I'm going to use to remember. Most of you would say associate, and that would probably be right. That's not the way I remembered it, because I looked at the word that perhaps you shouldn't say when you're looking at the rest of this and say, oh, there it is. If my stepson wasn't here listening to me record this, I would say it out loud, but I'm not going to say it right now. So when we talk about this word helps because if you think about it, you're always using sides of parentheses here. You're just moving parentheses. And when I think about it, well, if I have sides of a parentheses like this, it kind of maybe looks a little bit like sort of what we were talking about there. So if you're moving parentheses, just think about that. Maybe that'll help you remember it. Okay, distributive property you've absolutely seen. That's essentially when you've got a set of parentheses with 2 things inside of it being added or subtracted, and you have something on the outside, whether you're multiplying or in this case dividing. It just means that you distribute the multiplication to both things or distribute the division. And we've done tons of that in the past. I know you would have seen that in Algebra 1, but an example would be like if I've got 5 times 3 plus 6, I can take this 5 and multiply it times the 3 and multiply it times the 6. So this is the same as 5 times 3 plus 5 times 6, which would be 15 plus 30 or 45. Now, guys, I know you can do all of that stuff and it's fine. Most of what we're going to be asking you to use these with is that you're going to be identifying which property is actually being done as we look at stuff like this. So like for this exercise here, they've got a whole problem laid out for you and they're sort of talking about here's what we do and this is what happens next. Y'all, we're never going to ask you to do this. You're never going to have to do this. But the idea is identifying which property happened to make this happen. So we're going to kind of go through one at a time and see what goes on. So if I look here, I got numbers outside of parentheses. And then when I'm done, I don't have any parentheses anymore. That 8 has been paired with these two things. That 5 has been paired with these two things. Now, when we talk about something like that, if we have something outside of parentheses and it goes to two things, this is the distributive property. Now, I'm going to stop there because I'm recording this for time, but that's a place to sort of think about what we can do. Now, if I go down from here to here, what I have done is I have grouped 3 things being multiplied. I have grouped things together right there and right there to say that I can put those 2 things in a place where we can look at it. Anytime you're going to be bringing in parentheses to start, what you're going to be looking at is the associative property. Now I am going to write that because no matter how we remember it, putting the rest of this here does not get us in trouble, and that's important. Okay, at this point in time, with what I'm looking at right here, they just did the simplification. So we did that work, and then they just said 8 times 2 is 16, 5 times 3 is, we don't have to write that one down. So what I'm looking at now is the change from this step to this step. So when I look at that, well, it appears as though I have moved these 2 in order. So the 24 is next to the 5, and the 15x is next to the 16x. Now, we did this around a plus sign, so anytime I move something around like this around a plus sign, that is the commutative property because I commuted this from one side to another. Now this next one is tricky, but I really like it because the idea of this is both of these have an x. And so what they did is they said, well, if they both have that, that's kind of like saying I could bring that to the outside of parentheses and leave these in here. This is sort of like taking the distributive property and doing it in reverse, to go from 2 things with the same variable and then to bring that variable out and to leave things in parentheses. Whether you had parentheses and they go away, or you had no parentheses and you bring them in, this is still an example of, whoop, I did it wrong, sorry, I had the associative property on the brain there, the distributive property, because that is what we're going to be looking at. Now, in this case, we have now grouped 2 new things and we didn't have anything we took out of that. Anytime you're bringing a new set of parentheses in, that is something that we just took. This big thing plus these 2 is now these 2 being grouped together and they were not before. So that is the associative property. And then they just found the answer at the end of this. So that's what we're going to be looking at for that page and how we use these properties that we just talked about. Now I'm going to turn the page to the last one and we're just going to do these last 2 examples. And then I'm going to send you on your way and have you do your homework. Okay. So right now, this whole page is talking about the idea of being equivalent. Now, equivalent is a really interesting thing. It's the idea of 2 things not looking the same. Like I would say 7 equals 7. Those 2 things are flat out equal, 100%. Equivalent means that you've got expressions that look differently, like this one here and this one here. But if they're equivalent, we can put an equal sign between them by saying, while this is not exactly the same as this, they may very well be equivalent to each other. Now, equivalent means you can pick any number, plug it into both expressions here, and it should give you the same value to see what's going to happen. So one way you can prove that 2 expressions are equivalent to each other is pick a number. I like picking an easy number, like 0 or 1, because that gives us a way of sort of checking it. 1's a nice one, because 0 makes everything go away. 1 sort of gives us an idea of saying, okay, let's see how this actually works. And I'm going to substitute that in this entire expression here. So we'll have 8 times the quantity 2 times 1 plus 3. And if you see what I'm doing, I'm replacing every x with a 1, plus 5 times the quantity 3 times 1 plus 1. So that's this side. This one will be a lot easier. 31 times 1 plus 29. Now, I didn't put this equal sign yet because we still don't know. We're testing this. So at this point, we're checking this out. I'm going to do the easy math first because I'm a little lazy, and that's the way this goes. 31 times 1 is 31. 31 plus 29 is going to give us 60. So right now, we know that that is the value we get when we substitute 1 in on this side. We're going to check and see if we get the same thing. I'm guessing it's going to work, but let's see. So right now, we do the work inside parentheses, following order of operations. 2 times 1 is 2 plus 3. And I'll do the same thing here. 3 times 1 is 3 plus 1. Now I keep doing the work in parentheses. This will be 8 times 2 plus 3 is 5. This will be 5 times 3 plus 1 is 4. Now I do the multiplication. I can't add first. I multiply first. 8 times 5 is 40. 5 times 4 is 20. And we add the two of these together, we will also get 60. So right now, we have shown by example that the two of these are equivalent to each other. So that is a way that we can show that we're evaluating by the same value of x and they have an equal result. Another way that you can do this is actually by simplifying what you see on the left-hand side using our rules. And if you can make this equal to this using algebraic rules, then we can also say that they're equivalent. And so I'm going to rewrite this expression over here. 8 times 2x plus 3 plus 5 times 3x plus 1. And we're just going to go through some rules. If I can make it to 31x plus 29, we rock and roll. We're good to go. So I've got parentheses here. My first step is going to have to be to distribute in both cases because I got number on the outside of parentheses. It's what I've got to do. So 8 times 2x is going to be 16x. That plus is still there. 8 times 3 is 24. That plus is still there, so I'll keep it here. 5 times 3x is 15x, and 5 times 1 is 5. So I've gotten rid of the parentheses. Now what I have to do, you learned about yesterday, is the combining like terms. Actually, you remembered yesterday. You already knew this. 16x and 15x are like terms, and if I add the two of them together, I am going to get 31x. 24 and 5 are like terms because they don't have variables, and if I add them together, I'm going to get a positive 29. And holy math crap, Batman, that is the same thing that we have here. So by either way, we can say that either I plug the same value into both and they give us the same result, which gives us equivalent expressions or proves that, or I can take one of the expressions, simplify it, and make it look like the other one algebraically. Those are our two ways of showing that two things are equivalent. Now, if you look down here, it says constructing arguments. Now, we haven't talked about this a whole lot yet this year, but this is a way that we can talk about why you can say this is true. And you can say these expressions are equivalent because when I evaluate both for x equals 1, they result in the same simplified value. That's a perfect statement to use to be able to explain why this is true that we just did here on the side. Or we could say that these expressions are not equivalent because when I evaluate them both for a number, they result in different simplified values. And here's the thing that's great about plugging a number in. If you plug in a number and it doesn't give you equal values, and you did the math correctly, you have completely disproven equivalence. You can say there's no way this is true because by definition, if they're equivalent, they are going to give me the same thing no matter what number I plug in. That's the reason why you want to have this as an option. Now, we showed that they were equivalent in two different ways. So I could also have stated I used algebraic operations to show that one expression was in fact equal to the other. So the original one would have to be equivalent. But because they are in fact equivalent, this one here tells me that this statement patently untrue. And that is the way that we've got to look at that. So guys, that is what we're going to do for today. And that is the way that you do these problems.